Hi, I'm DJ Ware. On this episode of the CyberGizmo, I'm going to be covering process management. This is the third installment of the Linux internals right after this. So I was going to follow sleepy-eyed Vince. He had a suggestion that I should use binary for the numbering scheme, but I decided to keep it more conventional. And yeah, it's going to be Luke used the fork. That'll be the subtitle for this one today. So a process. How do we define one? What is it? It's any running program that's in memory. That's a process. It can be multiple instances of the same one. Each one of them is its own process. So it doesn't matter how many times you bring up your browser, how many copies you make of it, or how many copies of your file manager you bring up. Each one of them has its own unique place in the system. So yeah, and the shell, if you go to the terminal window, the shell is a process as well. So the way the shell works is that when you enter a shell command at the command prompt, it'll execute that command and then it passes control. So your screen, your keyboard all pass over to that program until it's finished. Once that program finishes, the control for your keyboard and your screen passes back to the shell. Now, there are foreground and background things you can do with the shell so that you can regain control and continue working, and then your process will go into the background. And then you can bring it back up with the foreground command. But, that's something else. That's not really for today so much. When a process is created, it is assigned a ID number, and this is called the process ID or PID. It is a unique number that's assigned by the Linux kernel. Every process has one, and the Linux will cycle through a number of numbers. So it doesn't just keep counting up forever. Eventually, it reaches a cap, and then it recycles back to the start again, and then starts issuing numbers again. Every process also has a parent process ID or PPID, except for one. The init process doesn't have one. And that is the only one that doesn't. So every process has a parent ID. When a process is loaded into memory, when it starts up or it starts to execute, there is a structure that is built. And that structure contains a stack, a heap, a data segment, and a code segment. So let's look at that. So I have a sample program here. This is a C program. You may not quite get it, but that's okay. For today, this is really, really going to be easy. So I have a number of things in this program. There is the main function. That's the entry point to a C program. This is where the execution begins. I then am declaring three different variables. Number one, number two, and sum, and they're integer, int. That's all you really need to know about this. When that structure gets built, after, this is a source code, this has to be compiled into executable, into a binary executable. And so once that happens, this is the structure that gets built when it loads. So there is the stack, and the stack contains, we'll talk about it. Let's just talk about in general what's in there. So those are variables that are created. And then you'll notice this white space. What on earth is that? So during the course of, it's kind of called the scratch pad area. I've heard it a lot of different ways you can talk about it, but it's just an area of memory that's set aside in case your program needs more. So if you're calling a lot of functions, or maybe you're allocating memory, that's the pool from which it draws and then allocates space from that. You're not allowed to be able to access memory anywhere outside of your program. If you do, you'll get a program fault. So, yeah, and then the second major structure is the heap. And the heap, we'll talk about what that has, but these two grow toward each other. The stack grows down from the top of the allocated memory, the heap grows up. So if they come in contact with one another, you get a stack overflow and the program exits, it's terminated. So you have to, this amount of memory you have, there's some variables that you can use to allocate additional space if you need it. But generally, this is set up by the compiler based on what it thinks you might need. And of course, you can change that. The data area is where I would have some other types of information that I'm storing off. And again, we'll talk about that. But that's your data area that's next. And then finally, the code area, which is the binary version of this stuff. That's where I'm going to start executing. There's some other structures as well, but we'll talk about those when we get to it. So what's in the stack? The stack is used for static memory allocation. So generally you would have the variables in the application would go into that. Heap is used for dynamic memory allocation. So and that is allocated above the data area, and it's known as the memory segment. Data stores any static or global variables if those are defined. There's also another area called the BSS, which is used for initialized static variables, but it's just really another type of the data segment. Code is the instructions of the program. There's like I said, there's other segments as well. So great, but okay, so I have this structure, but how does it get built? How does it get into memory? That's really the important thing, right? That's called creating a process. And there's a couple of ways you can do that. So the simplest method is also the wrong method to use, and I'll explain why. So you can use system. That's a call that you can put into a program. Now, some programs already have that built in and you can't do anything about it. But if you're writing your own code, you can create system, and you can just put the name of the command or the process or the program name that you want to execute, and it'll do it. It'll build it up into memory and it'll start it. The problem is that method is not very efficient. The second method is to use a fork and an exec. So let's talk about system first before we talk about the fork and exec. So system, what it does is it creates a sub-process running a standard shell. So it's gonna go out and it's gonna execute the Bourne shell or the C shell, whichever your default one is. That's the one it's gonna pick. So it's gonna fire that up. It's gonna pass command to that shell with the command that you're trying to execute. So the shell will pick that up. It will do all of its stuff that it needs to do in order to set up for that command to run, and it sits and it waits for the command to stop. When the command is done, the command returns control to the shell returns control to you, and then you can go on about your business. You can see that it's a lot of steps, right? So fork is the preferable memory method to do this because, first of all, it's more secure. Second of all, it's more efficient. And fork was really developed by, there's been operating systems that have used forking processes for a long time. You can go all the way back to Burroughs, and you can go back to some of the early IBM. They all have used some form of fork. Unix implemented it in a very unique way. At least I think it's very unique. I don't know of any other that quite did it the way Unix did it. So the way Unix was all about getting things done efficiently and quickly. Remember, I had said in one of my previous videos, it was all about response time. How fast can I get something done? So the way the fork works is that the process that is running, so let's say my program, that's my simple calculator program that just adds two numbers together and prints the sum. So that's running, and if there's a fork command in there, it just takes a copy of that program and creates another one, an exact copy. And the parent process doesn't wait. It immediately starts continuing on. And the process for the child process, it starts continuing on as well. But before we go into a lot of details on that, let's look at the process itself. So I have this is my program over here, the parent process. And in there is a fork. And that fork creates just a copy of itself. Now, the program counters are exactly in the same place because I have all of my state, all of my variables are initialized the same way. The program counters, everything is all as it was set when it encountered the fork. So the next line of code, both of these are going to execute is the statement after the fork. And it'll start processing down the line in parallel. And that's when you have to come in and figure out, Usually it's a get PID that you call in order to determine if you're the child or the parent, and then you decide what you want to do. But that's a programming lesson, and that's not for now. Let's just assume that the child process goes in a different direction and does something else from the parent process, which goes on about its business. So, all right, now I've got two things running. What if if I'm just doing concurrency, I want a second copy of the program up and they're both operating on different parts of the data stream. Great, I'm done. But if I'm trying to set up a new process that is completely different from the parent, let's say maybe I'm trying to call up VI or something, or maybe I'm trying to start up a video viewer. So how do I do that? The way you do it is through the exec function. In the child process, that would be the very next call once it's determined that, hey, yeah, I am the child process and I need to do this exec call. Sometimes you can use an exec directly, and sometimes you use exec VP, which is a little bit more simple way of doing it. But as soon as the child executes the exec process, it's done. That process, my numeric calculator that was there, it is flushed out of memory. It is gone for the child process. Now, the only exception to that rule is if the exec process fails and it passes back an error message, then you can find out what's going on and then maybe exit with an error message that, hey, I had a problem here. But if it passes and that exec goes through, my program that I was running, my calculator function, is replaced by whatever I call. It just sticks it right over top and gets rid of the calculator. So, and then it begins executing. Since there is no state that's been saved, it'll start executing like it was loaded new. So it starts over at the beginning of that new process and it starts to execute. And one other differentiator is that when I did the fork, there was another construct that was created, and that's called the parent process ID. And that always points back to the original parent, and that remains. So none of that will change. The process ID of the child remains the same after an exec. The parent process ID remains the same after an exec. So it continues to point back to the originator of the process that started up this child process to begin with. So here's my exec. This is what happens. So in this case, I'm firing up a file copy, and I'm doing an exec VP here. So my child process gets overlaid, and I have a new process after the exec. It doesn't make a copy. It just overlays it. So, okay, so I'm built. Now I'm executing. Now what? We enter what's called the process state machine. The process state machine is how Linux manages processes that are running, or maybe they're calling for an I/O and then they have to wait for the disk to load up the stuff into memory and then give me a pointer as to where it is, and then I go get it, and then I can reinstate the program and keep going again. Or maybe I've sent some data off to a graphics processor to render on the screen to maybe draw a sphere or to texturize it or whatever. But there is some management that's going on here. So the states of a process are new, which is when a new process is first created. Running, those are when the execution of the instructions in the program are being executed in sequence. Waiting, it's waiting for some event to occur. It could be an I/O, it could be some external event like a network. I'm waiting on a network packet to come in, or it could be a ready, which means that, okay, my internet's done. Okay, scheduler, put me back on a processor because I don't have one to execute. So it just says, hey, I'm ready to execute. Now the scheduler's got to get involved to actually go assign it back to a processor to run. Terminated, which means that I'm done, I'm closing out, and this is a signal to the scheduler to clear out all the memory and free up all the buffers and cache and all the stuff that needs to get done if the program created any in main memory. This hasn't got anything to do with the processor or cache. So this is what a typical process state machine would look like. So at the top left, you have new, and that would be the created state. And it enters, it goes to ready. The scheduler does some stuff. It figures out what processor to assign it to. It assigns that process to a processor, and then it switches into the running state. Your program begins to run until it's either interrupted or the scheduler says, "Okay, you've soaked the processor enough. I'm taking back control because I need to load another process to get it running." That's called, that's the whole thing that happens when you're in multiprocessing, is that you have to be able to share your processors with other things that are running. When it comes back, it goes back into it goes into a waiting state, and once the ready state is done, then you go into a ready state. So if you're just been thrown out of memory because you're waiting on something else to get out of your way, then you might just go sit and ready for a while until the scheduler gets back to you. But if you're waiting on an I/O, you're going to have to wait till that I/O completes before you can go back into a ready state. Now, the scheduler in Linux prefers to put you back on the same processor. Why would it do that? Well, it does that because of the performance enhancements that we all know about, right? So we have caching that's inside the chip, and that caching is assigned to each processor. Well, a portion of it is anyway. And then you have things like look-aside, you have branch order prediction, and all of those things that are set up for your program to run. So it's going to prefer to put you back on there. If it assigns a new processor, guess what? You get to start over again and build up all the cache and build up the branch predictors again. And so that's not a thing you want to have happen too much. So the scheduler in Linux prefers to put you back on the same processor. So you're going to sit in this kind of triangle here, running, waiting, ready, running, ready, just around and around and around until finally you've processed all the data, or your program is done and it goes to an exit. And at that point, the state is changed to terminated, and that's when that signals the scheduler to clean you out of memory and get you going, get you gone. So great, but that seems like a lot of stuff for the scheduler to have to track. How does it know how to track all that stuff? Well, there's structures that it creates, and it tracks everything that process is doing. But the other thing that is assigned to it is there's a priority that's assigned to that process as well. And the priority is used to tell the scheduler how often to give you preference for the processor. If you're running at the same process priority as everyone else, well, you get what you get when it becomes available. But if you set your process priority to a lower state, then what you're really telling the scheduler is, I don't need to run as often. I'm fine. I'm not a time critical task. I'll just take whatever I can get in order to get my stuff done. You can also make your priority a higher level priority, which means I need more processor. I'm critical. I have to get this done in a certain amount of time. So yeah, those are areas that will affect the scheduler. There's also address space assigned to the process to be able to say, where is it located in memory, right? And then what files that process is allowed to access, and that's based on your UID and your group ID. It might also be if you have some of the more advanced FACLs set on the file, but those are POSIX structures that it will also manage to determine whether you have access to a file or not. So the process can be a parent, it can be a child, and it can be a zombie. There's other ones it can be as well, but those are the three major ones. A zombie. Sounds like a bad movie, doesn't it? So the Linux maintains something called a process descriptor. It's really just a table. Now, this is not the process descriptor. If it was, it wouldn't fit on the screen. It's a much larger structure, but I'm just going to put in a few things and kind of give you a flavor of what it looks like. If you want more information, like I said, go out to the Linux Foundation. For every version, they have a lot of documentation on what some of the structures look like. You can also look at your user include files for these structures as well, if you choose to. So this is some of the information that it needs. The pointer at the top left, that is where the location in memory for the program is. The process state is running, ready, waiting, terminated, new, right? There's other ones in there as well. There's also some states where you can if you're controlling the program, or if the hardware is controlling part of the program, it can set it to uninterruptible, or interruptible. Uninterruptible means, hey, I'm not accepting any interrupts. I have a critical thing I have to do here. I'm just going to get it done. And maybe it's a state of code that's a particular critical function that's time sensitive. And so it'll turn off interrupts for that period, and then it'll turn it back on again when it's completed with that time critical piece. That happens. The program counter, where in the program is my current line that I'm executing. Some registers where the data that's being pushed back and forth into the processor for adds and deletes, or adds and divides, multiplies and subtractions. So yeah, those types of things. And then it has a list of open files. If you know about LSOF, that's the list of open files. So yeah, I realize this is a simplified view. That's why the ETC is there, is to cover all the rest of it. So anyway, yeah, if you're interested in that, you go dig into it, because we'd be here all night otherwise. All right, so we have a program, we have a process, and now we have it running, and it's starting to be swapped in. It's in the processor, and now the scheduler is pulling it out again. That's called a context switch. A context switch can occur several different ways. There are many ways that can trigger a context switch. The most common is that not all the programs will fit into memory. Duh. And so there is program code pages that get loaded into memory as they're needed. So as the program executes and it starts doing different functions, it'll load different different parts of the program into memory to run it. So there's a context switch that has to occur to allow that to happen. I'm replacing something with something new. I mean, I have an old code page that's in there, and I'm going to overlay it with a new one so that it can continue to run. So there's a context switch to allow the scheduler time to go do that. So all the context switch is the scheduler will save state on that process where it is right now. It'll then do whatever it has to do, and then it'll restore state, and then it'll tell the process to continue again. Context switches also occur if the machine is switching processors. So let's say you have a multi-core machine, and you have 4 cores. I get assigned to the first core, but when I get maybe I'm in a wait state, I'm waiting for I/O to complete, and I get ready again, and the scheduler goes to put me back on the processor, and it can't. There's something there that's already occupying that processor, and there's nothing left for me to be able to get in and start executing on. So it'll have to do a context switch in order to push me over to the other process. It already did the save state because it switched you out as waiting. So it had to do your save state already. So now it has to do a load on that save state, and guess what? You got to set up all the caches again. You have to relearn your branch predictions again on that processor. But that's what we call the time-wasting activity, and that's known as a context switch. I know it's valuable, but it is essentially anytime the processes are not executing the desired thing that you want it to do, it's wasting time managing the management part of the system. So it's also known as scheduling jitter. You might hear that term. I haven't heard that term in a long time, but I put it in here because from time to time I do hear people use that term. And so when you hear that, it's context switching is what they're talking about. All right, so we're done. We've gone through the 3 loops here, and we're getting ready to exit. We're getting ready to get fit to finish. Let's say that I have 2 things. I have my parent job here and my child process over here, and they've been executing independently. They're not even the same program anymore. This one got overlaid the child process got overlaid by an exec. So there's no rule that says that one has to finish before the other, but there is programming controls that you can put into the parent to hang around and wait for all the child. If you started up multiple child processes, you can hang around and wait until all the childs terminate. So, and that, or you can have this problem. The parent process is off running around, it hits an air condition and gets blown out of memory because it hit an error that was critical and it couldn't continue to run. So yeah, you have different orders of execution that you have to worry about. But so what happens when the parent process dies? That's really the question. And by the way, there's a number of wait commands. There's a bunch of them. But anyway, that's neither here nor there. But all right, so let's say the parent dies first, then it's gone. This is a bad problem for Linux, and it was a bad problem for Unix too, because what happens now is I have a child process that's running, and it's pointed back to the parent process that's gone. That process PPID number, it's invalid because there isn't anything there to receive it. Normally, a child process, when it exits, it will return a interrupt to the parent to say, "Hey, I'm done. I'm closing out." But in this case, there's nobody home. Somebody cut the phone line, so so it's no longer valid. So Linux knows about it. It knows about that. It knows that can happen. So what it does is the scheduler will say, the process ID is gone, and you have an invalid one. So it doesn't know what to assign you to. It doesn't, well, do I just pick a process at random and just say, okay, you can run from this one? No, it doesn't do that. That's what the init process is set up to handle. It's one of its functions. So the scheduler will assign the parent process ID to the init. And one of the functions in the init is called a zombie walk. Now, that's what it was called under Unix. I don't know what Linux calls it, but it was called a zombie walk. And a zombie walk is a section of code that just looks through and sees what child process has been assigned to it recently. There's usually a timer in there, because when the parent process went away, when it failed, there was an interrupt that was sent to the child and said, "Hey, your parent process just went down." And if you don't trap that and you don't handle it, then you're going to continue to run. And that's when the init process will say, "Oh, well, I'm going to give you a few cycles to kind of get your act together and get out of memory. And if you don't, I'm going to wipe you out. I'm going to just throw you out of memory and be done with you." And that's exactly what the zombie walk does. Is it comes through and it marks a flag and it says, "Okay, I want to come back again and see if I already have a flag on this." There might be a counter of 1, 2, or 3, and bang, you're out. That child process gets shut down. So yeah, that's how it cleans up after. And I don't know. Sometimes I have seen child processes attempt to. Now it's just an interrupt. So I've seen them try to avoid it, but those interrupts that the init sends, they start escalating to higher and higher interrupts until it hits a critical kill, which will blow your blow your program out of memory. So it will win eventually. It will win. I suppose probably the best thing to do is to show you how some of this works is actually go look at some examples. So let me go do that. Let me make this a bit bigger. Yeah, this is not my favorite thing when this happens, is that it doesn't automatically resize the window, but oh well, that's a new thing. I hope it changes soon back to the old thing. So let's do a PS first and see what we get. Now, as I've shown you a couple of times in the past, PS just lists, if I do it by myself, that's my processes that are running. So you'll see a PID here on the process ID. This is running and it's assigned to bash. And this is the PID that's assigned to the PS command I just ran that exited. So when I did this PS, the bash shell started up the PS command and allowed it to run. And then PS finished, passed control back to the shell, and I got my shell prompt back. That's what happened there. But what about if I want, now I'm going to pipe this to more. Piping is a feature of the internals we'll talk about in a future when we talk about IPC, what that is. But basically, I'm taking the output of PS, and I don't want it to just fly off the screen. I want to look at it a page at a time. So in this instance, I have the user ID, which is the user that started that particular process. And you can also list the group ID if you want. The EF doesn't do that, but there are some command options for PS that will. This is my process ID. This is my parent ID. And oh, look, there's init. And look, 0 is the process ID. It doesn't have one. So one line. And there's also this K threads. This is the equivalent init process for threads. All right. So it also has a 0. But that's a different topic. We're going to cover that one separately. So let's just go down through here. These are all system processes, and system things that are running. let's get down until we actually find something that's actually a program that's running. And finally, we have one. Well, not quite. I want to find one that's actually got, there we go. So there's AVI, and it's got 892, and the parent process is 842. So if I go back up here, maybe it will go back. No, it won't. But maybe I can just scroll back. So there's 842. There's the parent, and you'll notice that it is spawned from init. So this is probably a service. But anyway, so that's how the linkage occurs. This AVI is this one down here is probably a concurrency version of AVI. All right, so that's great, but that isn't really a lot of information yet, right? I mean, all I have here is the system time that it started. If there is a teletype device that's associated with it, that name would be in here. The amount of time that process has spent on the processor, and then the command associated with it. It's still not really a lot of information. So what about the running state? What if we want to really find out what's really going on? I can do a top, and top will give me some other information here, and you'll see that like the PID is here before. In this case, top is ordering this display according to the most active processes. So the first processes that lists are the ones that are currently executing. You'll notice the user, you'll notice this is priority. This is the nice increment, or I think it is nice increment, which is if there is something that is modifying the priority, that would appear here, and you'll see there's one right there that's modifying it. So yeah, so looks like 20 might be the default. Then we have the virtual memory, the resident memory, the shared memory, and then finally the state. And here we have a running, a sleeping, and then we have this one, which is idle. That stands for in this particular instance stands for idle. We didn't talk about idle. That's because top doesn't really follow what Linux calls things. Idle is just waiting, right? That's just a waiting process. Sleeping is also waiting. But there's some differences between idle and sleeping. Sleeping is waiting for an event to come back and trigger it. Idle just means it's just sitting. It's not doing anything. It has to be something that triggers it from either the kernel side or from a user application side that fires it up again. Percentage of the CPU, percentage of mem. If I do htop, I'm going to get probably fairly similar types of things. Yeah, in here, and there's my my state again. So yeah, it's not Linux is not really complicated. I wouldn't say it was complicated. I mean, you're into the more involved part of the system here. The process management is the core of Linux, besides the device drivers. Like I said, the process management schemes, the reason why I haven't touched the scheduler yet is because, really in depth, is because it's changed so much, and it continues to change based on how the different technologies that are coming into the processors, and Linux is trying to evolve the scheduler to exploit that, because the more efficient the scheduler is, I mean, remember, the whole purpose of an operating system is to get work done for you, right? Not be off just managing itself and twiddling its thumbs in the finger and in the corner and not doing anything, right, for you. So we don't want to spend a lot of time managing things. We want to make sure that we're done and we're moving on. So the next time what I'm going to cover is memory management, and I hope you enjoyed this today. I know this is somewhat introductory. If I go too deep, I know I'm just going to confuse a bunch of people. So let's just take this a step at a time, and we'll come down into it gradually. So consider this kind of a high-level explanation of process management. We did dive into it a bit. I mean, we are into the code of the programs because that's what it manages. You can't get away from that. That's what computers do. So if that makes you nervous and scared, I'm sorry, but that's the whole reason why computers exist, is to be able to execute instructions. So sorry about that. That is what they do. Anyway, hope you enjoyed this. Hope to see you all again real soon. Please like and subscribe. Bye for now.